Hi everybody. Today we're going to look at something called vectors, which turns out to be something very important in the idea of physics. To begin with, this is a map of Manhattan, and I don't think enough people appreciate just how amazing the grid system of Manhattan it is, and how easy it is to navigate your way around Manhattan because of the way it's set up, as opposed to maybe something like London, as you can see here, that might be a little more complicated to sort of get around. But as easy as it to get around Manhattan, let's say I needed you to meet me somewhere and you came in here to Grand Central Station. And I said, okay, once you get out of Grand Central, I need you to walk 11 blocks, turn, walk another 3 blocks, turn again, walk another 2 blocks, turn one more time, and then walk one more block. Well, even in Manhattan, with those kind of directions, you could end up in all kinds of different places, all over areas around here in the map. If instead, though, I said, when you come out of Grand Central, I need you to walk 11 blocks south. Then from there, I want you to walk about 3 blocks to the west. From there, 2 blocks north, and finally 1 block east. Well, then you'd find yourself meeting me here at the Empire State Building. Now, you might be annoyed with the somewhat roundabout directions I gave you, but at least you would get there. So what's the point? Well, it's the difference between what we call a scalar number and a vector. A scalar reveals something called magnitude. In other words, in those directions, the numbers 11, 3, 2, 1, those are all scalar numbers. A vector also reveals magnitude, but has with it direction. So that 11 south, that 3 west, that 2 north, that 1 east, those all have a direction associated with them. And it turns out direction is very, very important in physics and has a big effect on what you're doing and how you're solving things. So to start with, what we often have to deal with is more than one vector. We're not always concerned about what the individual vectors are, but what is called the net, the total of all those vectors. So we have to understand the idea of adding vectors together. Now to do this, I'm going to sort of set some rules that we're going to use throughout this and can be pretty useful in a lot of the physics that you do throughout the year. So over here on the right, I have sort of a compass here, kind of a north, south, east, and west compass. Now, for the sake of doing this and being consistent, I'm going to say that any vector that acts north or east is positive, and any vector that acts west or south is negative, kind of like you would do in a math grid. So here's the idea. You can represent a vector with an arrow. So here I have 2 vectors. And in this, I'm saying, okay, first I'm going to go 200 meters east. Now, when you add a vector to another one, you draw the next vector at the end of the first vector. So that means the 300 east, which would be a longer arrow because 300 is longer than 2, would begin at the end of the 200. Now, it's probably pretty obvious what the sum of these 2 vectors would be. If I start at the beginning of the first and go to the end of the second, that is the sum of the vectors, which of course would be 500 meters east. Now you have to have that east in there. That's an important part of the direction. Pretty simple, right? All right, well then let's look at another one. Let's say again I start off going 200 east. But 100 west, now I've got to begin at the end of the first arrow and come back the other way, because west is the other way. And again, the net, or the sum of those 2 vectors, is the beginning of the first to the end of the second, which would be 100 meters east. Now, sometimes I ask my students, well, what did we do here? And they say, well, we subtracted. No, we didn't. You only add vectors. You never subtract vectors. So what we did here, because 200 was east, it's a positive number, and I added to it 100 west, which is a negative number, giving me a net total of positive 100, which automatically means it's east by my rules. And you can do this with a lot of vectors. Okay, so again, if I look at this, now I don't have to draw arrows all the time for everything. Knowing the fact that north is positive and south is negative, I can add these vectors together here and say, well, 400 south, that's negative 400, plus 300 because north is positive, plus 400 because north is positive, plus negative 700 because south is negative. So again, I am adding the vectors together. And that gives me negative 400 as an answer. So really the answer is 400 meters south. See, I don't really need the negative here for this because the south is what's indicating negative. Okay, that's sort of a way to write that. Again, pretty simple, right? Well, until things start going in two directions, not just one. So if you go only north-south or only east-west, things are pretty simple. But in this case, I start off going 400 east. And then I go 200 meters north. Now again, if I'm drawing it, I begin at the end of the first one. Now, adding these two vectors together, I will tell you this. The answer is not 600 meters northeast. That is not the answer. That is not how we add the vectors. Because remember what I told you. To add vectors using arrows, I begin at the first one and end at the end of the second one. Well, look what I've drawn here. I've drawn a fancy thing called a right triangle. Most people know what's called the Pythagorean theorem, the whole thing that a squared plus b squared equals c squared. Okay. Well, I'm going to change that around a little bit because of what we sort of call everything here. The 400 meters east is known as the x component, component meaning part of the triangle. And so the 200 meters north is the y component of the triangle. And then in physics, we like to label this hypotenuse alongside r. R is a fancy word for what is called the resultant of the triangle, or in other words, I would just say the result of adding those two vectors together. Instead of a squared plus b squared equals c squared, here we would have r squared equals x squared plus y squared, the x component squared plus the y component squared. Now I only want r, so I would actually take the square root of both sides. So I like to just keep the equation like this. That's how I can get my resultant. So in this case, the resultant of these movements, 400 meters east and 200 meters north, would be the square root of 400 squared plus 200 squared. And I want to show you what this looks like on a calculator. So I've pulled up here a TI-89 on a computer that sort of simulates it. It's a pretty good graphing calculator. But for all calculators, before you do anything with vectors, there's going to be a couple things that are going to be important to do. And that is make sure you're in something called degrees. So if you see this RAD, which stands for radians, that's not where you want to be. So you have to click this mode button, and you want to scroll down to where it says radian. And scroll to the right and scroll down one and select degree. And if you hit enter, that will change that. Also for the 89, it can be very helpful, I've found, to be in what's called approximate instead of auto. It just helps a lot with a lot of things. So let's show how I could calculate that r in here. And I want to be able to do it sort of in one calculation. So I'm taking the square root of 400 squared plus 200 squared. So to do that, the square root is down here right above the time symbol. It's in blue. Anything in blue is a shift. So I'm going to start off and hit second, and that opens a square root, and it opens a parenthesis for me, which is really convenient. Then I'll type 400. Now on the 89, it doesn't have an actual x squared button. So to square something, you hit this caret and 2 button. That'll square it. Then you can do plus 200 caret 2. And make sure you close that parenthesis at the end and hit enter. Now you'll notice it looks exactly like it looks on my screen. Okay, and that's going to be really important to be able to look at that. Okay, so that gives me my answer, which is 447.2 meters, since meters is the unit here. However, there's a problem. I don't have direction. Well, oh yeah, I do. Look, you went north and east. This must be 447.2 meters northeast. The problem is northeast is actually a huge quadrant. So you could be, if you told someone simply to go 450 meters northeast, again, they could end up anywhere in that northeast area. So there's another important part of the triangle we need to account for, and that is the angle at which we're going. Now that's the Greek letter theta, which means the angle at which you're going, and that's an important part. Now, I could go through a lot of trigonometry with you to tell you all about these things called sine, cosine, and tangent. But I'm going to let a trigonometry teacher teach you all the nuances of that later on in your life. So for me, I'm just going to tell you how to do it. Calculating theta is using something called the inverse tangent of the y component over the x component. Inverse tangent is a function on your calculator. It's generally like a shift or a second or something like that. You should be able to find it somewhere on your calculator. It always says tan minus 1. Sometimes it may say arctan, but that's pretty much it. So in this case, I would put in the inverse tangent of the y value, which is 200, over the x value, which is 400. Okay, so let's look at how we would calculate the angle on this, which is the inverse tangent of the y value of the x, or in this case, the inverse tangent of 200 over 400. If you look here in the middle of the calculator above the YZT, you'll see in blue something called sine, cosine, and tangent, and then in kind of green, something inverse sine, inverse cosine, inverse tangent. We want that inverse tangent. So to get to that, it's this green button. So I want to start off by hitting the green button and this button, and that opens up inverse tangent with a parenthesis. I can then type in my values, 200 divided by 400, close the parentheses, very important, and hit enter. And there's my angle, 26.6 degrees. Degree is the unit of angle. So the answer to this is 447.2 meters, 26.6 degrees northeast. Okay. A little tricky, takes some practice doing. Really, it takes more practice doing it on your calculator than anything else. But that's how that's done. Okay, so now what if I have a whole bunch of movements? Like my friend, I was trying to get to the Empire State Building. And instead of wanting them to walk all around those blocks, I wanted the most direct route that you're going. In other words, in this case, if I was to say, okay, go 400 meters east, then 300 meters south, then 100 meters west, and then 200 meters north. Well, what I want is the resultant of all of those movements. In other words, I want this vector right here. Now, if I don't draw them to scale, I really won't know what the answer is going to be. So I have a little method that sort of will help us out here when we have these things. I like to create a little chart of what all the y movements are and what all the x movements are. Again, y movements are anything that are north and south. X movements are anything that are east and west. Now you might be wondering, well, why do I do y before x? Well, you'll kind of see as we do this. 400 east. Well, if I'm going east, I'm not going north or south. So there's nothing in the y. And east is a positive direction in the x. So I write plus 400. 300 south. Now south is a negative y direction, which means I'm not going in the x. 100 west. Nothing in the north-south. West is a negative number in the x. 200 north. 200 is positive in the y and 0 in the x. Now here's what this chart does for me. It gives me kind of a way of adding everything together. So if I add down the left-hand column, I get negative 100. And if I add down the right-hand column, I get positive 300. Now this tells me something right away. I have a negative y component. Negative y's are south. I have a positive x component. Positive x values are east. So I already know I'm going southeast, which kind of matches my little drawing there. The important thing here is these two numbers are my components, my x and y components. So now I just have to apply my two equations. The resultant, square root of x squared plus y squared. Again, I'm using those components. So the square root of 100 squared plus 300 squared. You notice I dropped the negative out of there. The reason I did that is when you square a negative, it automatically becomes positive. And there's some tricks with the graphing calculators that if you type in, for example, -2 squared, it will give you -4 because it's order of operation. So be really careful with negative numbers when squaring them. The number has to be in parentheses to properly square it, or you can just drop it like I did. So let's look at calculating this resultant really quickly. Again, on the calculator, it's always good practice. Start with, I want the square root of 100 squared plus 300 squared. Second, square root 100 caret 2 to square it plus 300 caret 2 to square it. Close the parentheses, hit enter, and I get 316.2 meters as the magnitude. Next, I have to do the direction, which is the inverse tangent of the y over x value. So the inverse tangent of 100 over 300. Now, that's one of the reasons why I like to do the y column first and the x second, because this is the inverse tangent of y over x. Directions are often given as y then x, like southeast. Again, you notice I dropped the negatives. Very important with the inverse tangent, you drop the negatives. Okay, so I want to do my angle here on the calculator. So that's the inverse tangent of 100 over 300. Again, inverse tangent is this green button. So I hit that and this to open up inverse tangent. 100 divided by 300. Again, make sure you close the parentheses. And there's my angle, 18.4 degrees. So the complete answer to this is 316.2 meters, 18.4 degrees southeast. And that's all there is to it. Okay. Again, takes some practice. So that's how to add vectors together that are only moving along the axes, north-south or east-west. Next time what we'll look at is when we're going to kind of move in all kinds of directions, as this example shows here. All right, see you next time.